So moving on to question 2. So question 2 is asking you why this is a redox. So lately I've had a look through the O-level syllabus. So it seems like they don't really do a lot of oxidation numbers in the new O-level syllabus these days. Yeah. But what I can tell you is that your examiners are not stupid. Okay, your examiners are not stupid. The people marking the paper are people who have done chemistry. Okay, oxidation number is one of those things that even though it's not stated in the syllabus, if you know what you're talking about and if you get it right, if you use it in explanation correctly, and I did say your examiners are not stupid, so do you think they will mark you down? Do you think that will be wrong? Any correct chemistry will not be penalized, you see. But when you start doing random stuff with incorrect chemistry, that is when you will be penalized severely, okay? So if you have learned it in school, I would strongly advise you to use it regardless, okay? Just like in maths, there could be more than one way of tackling a problem, yeah? It just depends on whether you use it correctly or not, okay? But I did say by referring to the equation. So, you see, the definition of oxidation and reduction in terms of oxidation number is very much the same as that oil rig, okay, where we talk about movement of electrons, where oxidation is loss of electron, reduction is gain of electron. When you lose electron, you lose your negative charge, right? Okay, so naturally when you lose electrons, this will mean that your oxidation number will increase. Because you lose negative charge, you will become more positive naturally, okay? When you gain electron, there's reduction, and reduction is also in terms of oxidation number is decreases. When you gain electrons, you gain negative charge. When you gain negative charge, your oxidation number will go and decrease in value. Even it could go from positive to negative, it could go from positive to 0, it could go from 0 to negative, okay? It decreases. Alright, so really they are related, okay? I don't know why they take it out of the syllabus, and can assure you, your examiners who are not stupid, they cannot mark you down if you used it correctly, yeah? So yeah, okay? So here we know that NO3 is nitrate, and nitrate is NO3 minus. As you will know it, HNO3 is H plus and NO3 minus. Okay, these are your vocabulary of ions, and you have two of it. Okay, the overall compound there has no charge, so that means therefore the nickel must be 2 plus. Why not nickel plus? Because you have two of it, so you have 2 times minus 1. Overall no charge, so you must have 2 plus, right? So when you combine these two together, the minus 1 and plus 2, the LCM is 2. You need 2 of it to balance out the charge. That's why you get this formula. So it goes back and forth, back and forth, back and forth, okay? You just need to think it like that. The oxidation state of an atom as an element. So oxidation state is of an atom. When you talk about oxidation state, is of an atom. But when that atom is an element, such as metal like this, they have an oxidation state of 0. Okay? So nickel 2 plus has oxidation state of plus 2 because it's an ion. Same deal there, okay? So it's Zn plus 2, okay? Because it's NO3 minus Zn2 plus as well. So in reality, so they want why is this redox? So they don't just want oxidation, they don't want just reduction, they want why is redox. So you have to refer to both, yeah? I'm going to use oxidation number first, and then I'll show you the one using electrons, yeah? The oxidation number of zinc, so we're looking at the zinc atom because oxidation number is for an atom, okay? Increases from, so you always got to specify from 0 in what species, in zinc, to plus 2 in ZnNO3 this is oxidation, okay? You can also talk about when you go from Zn to Zn2 plus, you can write this equation. Loss of electrons, zinc is oxidized. Alright, it increased in oxidation number, loss of electrons, zinc is oxidized. The other equation will be nickel 2 plus 2 electrons give you nickel. Nickel gain electrons, nickel 2 plus, no, sorry, oxidation number, okay, oxidation and reduction refer to the species, sorry, nickel 2 plus is reduced. Okay, so I'm going to talk about oxidation state again here. So there are two alternatives there, so whichever one you've been taught in school, I'm sure will be alright. So I talk about the oxidation state of nickel because it's of the atom. It decreases from +2. Now I talk about the species, which is from nickel nitrate, nickel 2 nitrate, to 0 in nickel. This is reduction. So I have shown that both reduction and oxidation happen in the same reaction. So it is a redox. Okay. Next bit, the ionic equation. These are two half equations. Why did I not show the nitrate? Well, because the nitrates are what we call spectator ions. All nitrate salts are soluble in water, so they are going to give you 2 NO3 minus. That means you have 2 of it. Here they will also have 2 NO3 minus. Oh, you have NO3 minus on both sides. They just dissociate, in equal amount. So you can cancel them out. They are spectator ions. Or from these two half equations, what you can do is you can tell 2 electrons there, 2 electrons there. The LCM is just 2, so you don't need to multiply any of this equation by anything. You can just add them up together, and you will get the complete balance equation. So because the electrons cancel out there, there's nickel plus zinc 2 plus. Okay, so now the zinc is metal, so they don't dissociate. Nickel is also metal. The nickel 2 plus and the zinc 2 plus are aqueous because they are soluble in water. All nitrates are soluble in water. Okay, where's the water coming from? Well, what does aqueous mean? Aqueous means you dissolve in water. Okay, now you want next a label diagram. How? When you have a fork made of nickel, you want to electroplate with silver. You want to deposit. So electroplate means you want to deposit silver, okay, onto the spoon, onto the fork. Okay, you want to deposit silver onto the fork. What is your half equation? Your half equation is you go from silver plus, you add electron because silver 1, you just add 1 electron, you go to that. Where do you want this to happen? Where do you want this to happen? I want to deposit silver solid. Therefore, I start from this electrolyte. This is soluble in the electrolyte because that's the only way the electrons, the ions can move around, right? Okay, this is reduction. Where do we want reduction to happen? Well, I want to deposit silver to cover the fork made of nickel, right? But it involves a reduction. Reduction happened at cathode. Okay, and what is reduction? Well, reduction we talked earlier was reduction involved gain of electrons. Reduction involved oxidation number being decreased. Well, reduction is gain of electrons, reduction at the cathode. So this must happen at the cathode. All right. So, so what do we have? We must have an electrolyte. Okay, we have got to have an electrolyte. So this will be your soluble source of silver. So it can be silver plus aqueous. Actually, you could also use silver nitrate. In fact, that is soluble, right? All nitrates are soluble in water. Okay. So you will have your fork. I can't draw a fork very well, but anyway, I can try. Okay, there's your fork. All right. We need some electricity. Okay. The thing is, this has to be cathode. This has to be the cathode. All right. What else? I think I also want this to be silver, or you can say Ag, solid. We are going to transfer the silver, the pure silver there, onto there so that it will cover the rest of it. Now you need to be careful with this, all right? So cathode attracts cations, so cations are going to go there. Ag plus electrons will happen here, whereas there's cathode, right? Cathode attracts cations, so cations go to cathode. Cations are positively charged, so cathode is negatively charged, which means I've drawn this incorrectly. Okay, I've drawn this incorrectly. It should be negative there and positive there. Okay, short one for negative, and negative is cathode there. Okay, so you need to be careful including every single bit of your diagram. Yeah, this is your silver electrode. It's actually anode. Okay, it's actually anode. And you want that to be dipped in the electrolyte like that. Okay, so that can conduct electricity in a soluble salt. Yeah, so it's gonna overall it's gonna it's not gonna do anything on the electrolyte. At the anode, this is what will happen. This will go to Ag plus electron. So what happen is that will get oxidized and release the Ag plus in the solution, which go to the cathode and gain electrons and deposit silver around the fork, and they will do the electroplating. Yeah, terminals are important. Labeling cathode and anode. Okay, so the anode is a plus there. All right. In this case, you don't get the anions going here. In fact, because this is electroplating, right? So here we get cations going to the cathode, but here we still see oxidation at the anode, which is loss of electron, increase in oxidation number from 0 to +1. All right. Next bit, aqueous ammonia is added to zinc ions until no further change occurs. So this is in your paper 3, qualitative analysis. So remember, you are in paper 2 or paper 1. In theory paper, you do not have access to that table of results. So you need to know your observations. Yeah. Okay. So what will happen is, ammonia is a weak base, right? So ammonia in water dissociate partially into OH minus in water. It's a weak alkali or a weak base. I'm sure you know how to write the equation and how to define it. Okay, the presence of OH minus with zinc ion is that you are going to get a white precipitate first. It's a result of the formation of zinc hydroxide, zinc 2 hydroxide. Yeah, but they want observations. So a white precipitate. So you should use full word because you are no longer in paper 3, for example. Okay, so you shouldn't use PPT. A white precipitate is formed. And then because you're looking for observations, and then you also need to have a look at this until no further change occurs. So as you know, in your practical, you're supposed to add, and then think about what happened in excess, right? So here, you need to think about what will happen when you have excess NaOH. When you have excess NaOH to zinc 2 plus, what would you get? All right, would it be soluble or would it be insoluble? So the white precipitate is formed in excess NH3. The white precipitate will dissolve, and once it dissolves, what do you see? Once it dissolves, you get a solution. It's no longer a precipitate, and then colors are very important. But here, you know, the zinc don't form colored ions, so they just give you colorless solution. So you know all this from your practical actually, but you know, the theory, then it comes from practical as well. Yeah, okay. Next bit, blocks of zinc are attached to the underside of sheath metal iron to stop them from rusting. So this is a bit of sacrificial protection there. How zinc stop the ship from rusting? Explain how, right? Okay, so in the reactivity series, in the metal reactivity series, so you know zinc is a more reactive metal than iron because it is higher up in the reactivity series than iron, right? In case you don't know, potassium, sodium, magnesium, calcium, it's potassium, sodium, calcium, magnesium, aluminium, zinc, iron. Here there's the relationship there. Okay, so there is more reactive metal. So zinc is a more reactive metal than iron. Therefore, zinc would preferentially be oxidized, because we're talking about rusting, right, which is basically oxidation in air, or oxidation in air by O2 or by oxygen. Okay, then iron. Okay, therefore the iron underneath won't rust. So the iron is covered by a layer of zinc, right? So it will be the zinc that forms zinc oxide, and iron underneath won't rust. So they oxidize in air. So basically you get zinc plus O2 give you ZnO, because Zn2 plus O2 minus. So you should know the correct formulas like that. And any equation you write, oxygen is O2, here's only one oxygen, which means it's not balanced. So don't forget to balance your equation. Yeah, whatever you do not forget to balance the equation. All right. What's next? Name the electrolyte used for this reaction. The copper made by this is impure. So this is about purification of copper. And not a lot of the time I said a lot of things is case study, right? When I say case study, basically when you revise through the thing, right? You go through the syllabus. That's what I'm talking about. You need to know everything that's stated in the syllabus, right? Purification of copper is something, okay? You use impure copper anode, and then that will transfer into pure copper cathode. So your cathode become bigger, your anode becomes smaller, but you also need the presence of aqueous copper 2 sulfate as the electrolyte. It's blue, your color will not change because the amount of water doesn't change, the amount of Cu2 plus doesn't change. It's just a transfer of copper from the impure anode to the pure copper cathode. I think I mentioned that just now. You're lucky here, they actually tell you that negative electrode is cathode. Cathode is negative electrode because it attracts cation. Cations are positively charged. Reduction happens at cathode, that's why I deposit pure copper at the cathode. Yeah, so pure copper, impure copper. Impure copper is very important here because guess what? They actually tell you this is the objective. So you gotta read the question carefully. Yeah. So write the equations. So reduction happen at cathode, where the cations go to. The cations go to cathode. Reduction is gain of electron. Oxidation is loss of electron. So oxidation happens at the anode. So that one will give you copper. And then the Cu, the impure copper, will dissolve into the electrolyte to give you the Cu2 plus and then 2 electrons. So loss of electrons. Increase from 0 to plus 2 in oxidation state is also oxidation. Not sure you do oxidation number anymore in O-level, but you should have. I mean, it's a correct chemistry thing, and even though it's not in the syllabus, I still believe oxidation number is an important thing to teach and to learn in O-level. Yeah.